Hi. So today I'd like to talk to you about generators and motors, which is an application of Faraday's law, which we've been discussing in previous lectures. So electric generators, they take in energy by work and transfer it out by electrical transmission. An AC generator consists of a loop of wire rotated by some external means in a magnetic field. The external means could be wind, water, or steam in different power plants. Of course, wind could come from wind turbines, and the water could come from falling water at a dam in a hydroelectric plant. And then in fossil fuel plants, what they generally do is they burn the fossil fuel, and the heat from the burning heats water, which is converted into steam. The steam moves through, and then the steam turns the turbine. So any of these means are examples of how you could have an external agent causing the rotation. The basic physics of how it works is, of course, Faraday's law. So here is a schematic of the loop in an external magnetic field. The magnetic field here points right, as indicated by the green arrows. The loop, this is a kind of cut version of the loop. It has an area vector, indicated in black here, which points perpendicular to the plane of the loop, which is in gray. Now, the area vector makes an angle theta with the magnetic field. This angle theta, because the loop is rotating, is going to be a function of time. Theta is equal to omega t, where omega is the angular velocity and t is time. Remember that you can write the angular velocity omega as 2 times pi times f, where f is the frequency of rotation. The SI unit of frequency is the hertz, which is 1 over seconds, and so f is going to be the number of rotations per second. If you do this, then you can calculate the magnetic flux going through that loop. Remember that the magnetic flux is defined as the dot product between the magnetic field and the area vector, B dot A. The magnitude of this would be BA cosine of theta. And of course that would give you a function for the magnetic flux of BA times cosine of omega t. Now, Faraday's law says that the induced EMF in the loop will be equal to negative n times d phi dt. Here, n is the number of turns of wire that you have in the loop, and then d phi dt is the time derivative of your magnetic flux. Now, going back to the previous slide, remember that phi was equal to BA cosine omega t, and when you take the derivative and plug everything into this equation, that ends up with an induced EMF of NAB omega sine omega t. To remind you yet again, n is the number of turns, A is the area of the loop, which doesn't change, only the angle between the loop and the magnetic field changes, not the magnitude of the area itself. B is the magnetic field, whatever that might be, and omega is equal to 2 pi times f, where f is the frequency of the rotation. Now, of course, this is a sinusoidal function. The max of the sinusoidal function will be when sine goes to 1, and that gives us NAB omega. Okay? So, this gives us an AC induced EMF, or an induced current. Let's do an example problem. Your camping buddy has an idea for a light to go inside your tent. He happens to have a powerful horseshoe magnet that he bought at a surplus store. This magnet creates a 0.2 Tesla field between two pole tips that are 10 centimeters apart. His idea is to build a hand crank generator with a rotating 5 centimeter radius semicircle between the pole tips. He thinks you can make enough current to fully light a 1 ohm light bulb rated at 4 watts. Find an expression for the induced current as a function of time if you turn the crank at a frequency f. Assume the semicircle is at the high point at t is equal to 0, and what frequency will you need to turn the crank for the max current to fully light the bulb? Okay, so there we have it. Now, that's from our supplemental textbook, which is Night, and it's in chapter 34. Now, associated with this problem is a figure shown here. So let's discuss the figure for a second. First of all, the blue dots in the figure are the magnetic field, which is pointing out of the screen at you here. The magnitude of that magnetic field is 0.2 Tesla. Now you can see that you have this funny looking top part here, which is a wire, and at the top of that wire it's bent into a semicircle. And the radius of the semicircle part has a 5 centimeter radius. Now, when it's at the top position, you can see here that the area of the loop is maximized It's basically a square with a semicircle sitting on top of it. When the loop is at the bottom, it'll be a square with a semicircle cut out of it, and that'll be when the area is minimized. So you might think that this is a completely different situation from what I was talking about before, but actually it's pretty similar. What you've got going on here is basically a circle, right? That's changing its flux, right? The rest of this flux that's in the plane of the loop at all times, that's just a constant that's sitting there all the time. And since it's not changing, it's not going to factor into our induced EMF. To understand what I'm talking about, let's look at the sketch that I made here on the next page. If you plot the magnetic flux, it's going to look like this. It's going to look like a sinusoidal function here, or actually a cosine function, that's sitting on top of an additive constant. I've called this additive constant here phi naught, and it's where the center, if you draw a line through the center of that sinusoidal function, that would be it. Now, I don't know what this phi naught is, but I don't have to know, because what I really need is d phi dt to get my EMF, and of course, when you take the time derivative of a constant, it goes to 0. So, what happens is, it told us in the problem that the flux is going to be maximized, or the circle is going to be at the top at t is equal to 0, and that's when the flux is maximized. So I've drawn that here, and then of course it'll go to its minimum value of the flux when your semicircle is down at its bottom position, okay? And then it'll go back up when it's at the top, okay? Now the period of this motion would be 1 over f, which we don't know, but which we're going to solve for later. And so it'll take the period, 1 period, to get from the max flux back to the max flux again. So if we're to plot this out, then the flux as a function of time would equal to phi naught plus BA cosine omega t. So basically, it's really similar to what we were talking about before. And the area here is the area that's changing, which is the area of a circle, right? And of course, the circle is going to be added into the area when the semicircle is at the top, and then you have it cut out when the semicircle is at the bottom. I hope that makes sense. So here, I'm going to say that I basically have the same condition as the previous problem, where the number of turns in this case is 1. Okay, so my induced EMF is going to equal to the current times the resistance of that loop. Okay, this is Ohm's law, so EMF is equal to IR, which is equal to minus d phi dt. Now, n is 1 here. There's just 1 turn, so I don't have to worry about that. And then when I take the derivative of my function for my flux, I end up with BA omega sine omega t. All right, now plugging in some numbers, B is equal to 0.2 Tesla. The area that's changing is pi r squared, where r is the radius of my semicircle, right, which is 0.05 meters. Omega is equal to 2 pi f, which I don't know. I have to solve for that, so I leave it as a variable. And R is equal to 1 ohm. They told us that in the problem, that the effective resistance of everything was 1 ohm. So if I use that, I can solve for my current, which is what the problem asked for. I'm just going to divide both sides of this equation by R to get it in terms of the current. So I of t is going to equal to, plugging in for all those numbers, 9.87 times 10 to the minus 3 coulombs times F times sine of 2 pi ft. Okay, now you might be saying to yourself, how does she know that's coulombs? Where did that come from? Well, it's a current, right? And so what I end up with here out front of my sine function is a number times the frequency, right? Well, a current is an amp, which is a coulomb per second. So I know that my constant here has to be in coulombs if I've put everything in SI units and been responsible, because 1 amp is a coulomb per second, and frequency is 1 over seconds. Okay, now, it wants to know what the frequency would be if I work at the max power, or the power of the bulb. The power of the bulb was given as 4 watts, and the equation for power is I squared R. So I have my I max here, right? Of course, the power would fluctuate as the current fluctuates, or as the current squared fluctuates, excuse me. But the maximum value will just be the coefficient that's multiplying this sine function. And so that's going to be our I max, which I'll square. And then I max is 9.87 times 10 to the minus 3 coulombs times F. So I have 4 watts is equal to 1 ohm times 9.87 times 10 to the minus 3 coulombs squared times F squared. And now I can use this expression to solve for F. I divide through and solve and get F is equal to the square root of 4 watts per ohm divided by 9.87 times 10 to the minus 3 coulombs squared. When I plug all this into my calculator, I end up with 203 hertz. So that's my frequency. Oh, the problem also asks if that's feasible. No. I don't think that you're going to be able to turn a hand crank generator 203 times per second. Do you? No. So you can tell your friend not to waste his time. All right, let's talk about motors. I'm only going to talk about these briefly. On your course website, I've included another link that includes a very nice animation that I want you to look at. So I'm just going to touch on the concepts here, and then I'm going to let more explanation take place in that other external YouTube video. So here we go. Motors are kind of the reverse of a generator, right? In a generator, you put in motion and you get out current. In a motor, you put in current and you get out motion. So motors are devices into which energy is transferred via electrical transmission while energy is transferred out by work. Like I said, a generator in reverse. So the current is supplied to the coil by a battery or some other external supply, and then there's a torque acting on the current carrying coil that causes it to rotate. So looking at this a little more closely, here's a schematic where you've got the north and south pole of a magnet generating a magnetic field that goes to the right here. Now you have a coil that's rotating inside of this field. Okay, it's drawn here, and you can see that the current goes up on the left-hand side of the coil, goes over the top, and then down on the right-hand side. Now remember, we have the Lorentz force law, which is, in this case, F is equal to IL cross B. So if you were to do it, for the current on the left, you would have IL cross B, and you would have a force into the screen. And for the current on the right, same idea, except now the force, that's really hard for me to do, okay? The force is out of the screen coming at you. Since you have a force going in on one side and coming out on the other, it causes it to turn, right? So it causes a torque. Remember, your equation for torque from introductory physics is R cross F, okay? All right, so in other words, rotation happens when you put that coil inside of the magnetic field. Now, from that rotation, you can do useful mechanical work, and it can be done by attaching the rotating coil to some external device. Of course, when that happens, as the coil rotates, you are going to induce an EMF, and this is called a back EMF. And the back EMF is going to increase in magnitude as the rotational speed of the coil increases. So I guess there's a downside, okay? The current in the rotating coil is limited by that back EMF. And the induced EMF explains why the power requirements for starting a motor and for running it are greater for heavy loads than light ones. Now, like I said earlier, I'd really like you to watch an animation which explains better how motors and generators really work and includes a discussion of commutators and things like that. And so I've included a link on your course webpage and here in this video for any of you that are interested of a YouTube video that I really liked that showed a nice animation of how motors and generators work. Other than that, if you have any questions, let me know, and I'll see you around.